In this podcast episode, Chris Cottrell, a science educator with over 2 decades of experience teaching environmental science and earth systems in coastal Georgia, shares his deep interest in a fascinating geological mystery, the Carolina Bays. The Carolina Bays are elliptical depressions scattered extensively across the eastern coastal plain of the United States, stretching from just below New York down through the Carolinas and Georgia, with sparse occurrences in Alabama and a surprising resurgence in Nebraska. These formations are remarkable for their consistent elliptical shape and orientation, which intriguingly points toward the Great Lakes region of Michigan. Chris explains that these bays are not merely random depressions, but mathematically precise ellipses, a fact confirmed by extensive measurements conducted by researchers like Michael Davis, who has cataloged over 70,000 such features. This widespread distribution and uniform orientation suggest a common origin, yet the bay's exact nature remains elusive. Their elliptical rims and raised edges distinguish them from other similar geological features, making them a dominant and mysterious presence on the landscape. Chris emphasizes that despite their prevalence, these formations are often overlooked in academic literature and mainstream geology, underscoring the need for renewed scientific attention. The origins of the Carolina Bays have been debated since their discovery in the 1930s, initially thought to be meteor impact craters due to their shape and distribution. Early aerial surveys led scientists to speculate about a cosmic event, but the absence of meteorite fragments shifted the consensus toward terrestrial explanations. The prevailing uniformitarianism perspective posits that these features formed gradually through natural processes such as wind and water erosion, rather than sudden catastrophic impacts. Over the decades, various hypotheses have emerged, ranging from beaver dams and spring basins to oriented lakes formed by permafrost thawing in Arctic regions. However, none of these explanations fully account for the bay's perfect elliptical shapes, raised rims, and consistent orientation. Chris critiques the dominant wind and water hypothesis, noting that it relies heavily on outdated experiments and fails to replicate the bay's unique characteristics, leaving the mystery unresolved. A significant part of the discussion focuses on distinguishing Carolina Bays from other oriented lakes found worldwide, such as thermokarst lakes in Alaska and play lakes in Texas. These lakes often form in permafrost regions or areas with specific hydrological conditions, but they lack the precise elliptical shape and raised rims characteristic of the Carolina Bays. Chris points out that while these other lakes may superficially resemble Carolina Bays, their formation processes and environmental contexts differ markedly. Using modern tools like LIDAR and Google Earth, researchers can analyze the terrain in unprecedented detail, revealing the distinct morphology of Carolina Bays compared to other features. The bay's shallow centers, sharp rims, and uniform orientation set them apart, reinforcing the argument that they are not simply products of wind and water, but likely the result of a more complex, possibly catastrophic event. Chris advocates for a cosmic impact origin of the Carolina Bays, proposing that they resulted from a massive comet or asteroid striking the Laurentide Ice Sheet over the Great Lakes region. This impact would have ejected enormous fragments of ice into the atmosphere, which then re-entered the Earth's surface at an angle, creating the elliptical depressions observed today. This theory explains the bay's orientation toward Michigan and their consistent shape as conic sections formed by oblique impacts. The ice ejecta hypothesis accounts for the shallow depth and raised rims of the bays, suggesting that the ice fragments were not solid blocks, but highly fractured masses that dissipated energy upon impact. Chris contrasts this with other models that envision solid ice chunks creating the bays, arguing that glacial ice's plasticity would result in different impact dynamics. This catastrophic event theory challenges the conventional gradualist views and aligns with the bay's widespread distribution and uniform characteristics. Despite the compelling nature of the cosmic impact hypothesis, direct physical evidence remains elusive. Chris recounts fieldwork involving excavation of Carolina Bays with heavy machinery, sediment sampling, and collaboration with comet research experts to detect magnetic grains or cosmic materials indicative of extraterrestrial impacts. Initial tests yielded inconclusive results, partly due to the high costs and technical challenges of analyzing samples for rare cosmic markers like nanodiamonds or platinum. The difficulty in finding definitive impact evidence is compounded by the nature of the bay's formation, where ice fragments would melt, leaving little trace of the original impactor. Chris highlights the need for more targeted research and funding to explore the bay's centers thoroughly, suggesting that current scientific efforts have been insufficient and that the bay's true origins remain an open question. The conversation touches on the Younger Dryas, a well-documented period of abrupt climate change approximately 12,800 years ago, often linked to cosmic impacts. While some researchers, including Antonio Zamora, argue that the Carolina Bays formed during this time due to ice ejecta from impacts on the Laurentide Ice Sheet, Chris expresses skepticism about this timing. He notes that the bay's distribution and geological context suggest they may be much older. Nonetheless, the Younger Dryas event provides a useful framework for understanding how multiple airbursts and bolide impacts could have influenced Earth's climate and geology. Chris references evidence of platinum and nanodiamonds in Younger Dryas sediment layers, supporting the idea of widespread cosmic activity during that period, though not necessarily tied directly to the Carolina Bays formation. A breakthrough in studying the Carolina Bays has come from the use of LIDAR, light detection and ranging technology, which allows for high-resolution mapping of terrain beneath vegetation and urban development. Chris praises the work of Michael Davis, who has utilized LIDAR data to map tens of thousands of Carolina Bays across the United States, revealing their true extent and precise shapes. LIDAR's ability to penetrate dense foliage and highlight subtle topographic features has revolutionized the understanding of these formations, showing that they are far more numerous and widespread than previously thought. This technology also helps identify ancient shorelines and barrier islands, providing context for the bay's age and preservation and challenging existing geological models. Chris delves into the geological history of the eastern coastal plain, discussing ancient shorelines and barrier islands formed during interglacial periods when sea levels were significantly higher than today. These paleo shorelines, dated to around 125,000 and 400,000 years ago, serve as benchmarks for understanding the age and preservation of Carolina Bays. He points out that Carolina Bays are notably absent below these ancient shorelines, suggesting that rising sea levels during interglacials would have eroded or submerged any bays in those areas. This observation implies that the bays must predate the last major sea level rise, pushing their formation back hundreds of thousands of years, far earlier than the Younger Dryas. This geological evidence supports the hypothesis of an older, possibly mid-Pleistocene origin. The dominant academic explanation for the Carolina Bays remains the wind and water hypothesis, which attributes their formation to katabatic winds blowing off glaciers, shaping shallow ponds into elliptical forms over thousands of years. This theory, rooted in a 1977 PhD dissertation by Ray Kozowski, has been widely accepted despite its limitations. Chris critiques this model for relying on oversimplified experiments and failing to account for the bay's uniform orientation, raised rims, and sheer number. He argues that the wind and water hypothesis cannot adequately explain the bay's precise elliptical shapes or their distribution, advocating instead for a catastrophic impact origin. This ongoing debate highlights the need for multidisciplinary research and modern analytical techniques to resolve the mystery. The discussion broadens to consider the role of cosmic impacts in Earth's climate and geological history, drawing parallels between the Carolina Bays and other known impact events, such as the Chicxulub crater that contributed to the dinosaurs' extinction. Chris emphasizes that impact events, whether singular or multiple, have shaped Earth's environment, influencing sea levels, climate cycles, and biological evolution. He also touches on the Milankovitch cycles, variations in Earth's orbit and tilt, that govern ice age rhythms, noting that impact events may have interacted with these natural cycles to produce abrupt climate changes. Understanding the Carolina Bays within this broader context could shed light on the interplay between extraterrestrial forces and terrestrial geology. Concluding the conversation, Chris expresses hope that renewed scientific interest and technological advances will lead to a better understanding of the Carolina Bays. He calls for more comprehensive field studies, interdisciplinary collaboration, and the application of modern tools like LIDAR and computer simulations to test competing hypotheses. Chris also highlights the importance of engaging new generations of geologists and researchers to revisit this long-standing mystery, emphasizing that the Bay's enigmatic nature offers a unique opportunity to explore Earth's history and cosmic interactions.